Okay, we'll continue looking at some applications. This time we're going to look at some geometric interpretations of the determinant. And here we'll start right off with the area of a triangle. And this is kind of interesting. The area of a triangle whose vertices are given. We have three vertices of the triangle. Then you can find the area by computing this determinant. You can see here where the first coordinates of the first vertices x1, y1 are there, and then a 1, and then the second coordinates in a 1, and third coordinates in a 1. Kind of an interesting matrix. Take the determinant of it, and then you multiply it by plus or minus a half. Now, what do you mean plus or minus? Well, you choose either positive or negative in a way to make the area positive. So there's times when this determinant can come up to a negative number, and then you would multiply by negative 1/2. Of course, the area should be positive, but it works every time. And that's kind of cool because if you think about, an arbitrary, if I give you 3 points, and I say, okay, let's find the area of this triangle in general, how are you going to have to do that? I mean, you can use the distance formula for the distance between these 2 points to find this side length. But then you need the altitude, and you can't, if you have the 3 side lengths, I guess you can use Heron's area formula, if you remember that one from trigonometry or geometry. So, but you'd still have to compute these lengths for all these, which would be computations. And then another way is obviously using like law of cosines or something to find these angles, one or more of these angles, and then use trigonometry. But still, that's a task. And here it's pretty quick. It's fairly quick. I mean, you've got a 3x3 determinant to find, but it doesn't take that long. And so it's a pretty powerful thing, I think. Now, I'm going to do the proof of this. Little bit tedious in terms of the algebra, but we're going to do a proof of this. And in order to do the proof of this, we need to know actually about the area of not a triangle, but a trapezoid. A trapezoid is a quadrilateral, and it has 4 sides, and it has 2 sides that are parallel to one another. Okay, the other 2 sides may not be. Okay, so rectangles are trapezoids, but not all trapezoids are rectangles like this one here. So the question is, what would this area be of this trapezoid? Let's suppose the distance between the 2 parallel sides is h, and then this side length here is, say, little b, and this side length here is big B. Okay, so what would the area of this trapezoid be? Some of you might have the formula memorized. That's fine. Let me give you a little help here. If I sort of draw this diagonal from this vertice to this vertice, I've divided the trapezoid up into what? 2 rectangles, right? 2 rectangles. Rectangle 1, notice this is 90 degrees here, right? So we have 1/2 b little b h for the area of that one. The second one, right? This is a right angle here now, and so we have big B is the base, and again h is the height, so 1/2 big BH. And so typically a way to write this is factoring out the 1/2 and the h and writing it something like this. Okay, and of course if little b and big B are equal to one another, then in that case we would have a rectangle. And notice what happens. Let's say big B and little b are both little b. We'd have 2b times 1/2 is just BH, base times height, which is the area of a rectangle. So it makes sense. Okay, at any rate, we're going to use this in the following proof. So we start with setting up a coordinate system here to give us reference. And let's suppose our points are as follows. So this point right here is the point x1, comma y1, right? And the other points, I'm going to put actually maybe over here, x2, and of course its height is y2. I'll just say this is the point x2, comma y2. And then up here we'll put the final point here, x3, comma y3. Okay, so it's coming down. So I'm going to put x of 3 in between, and there's nothing to say, that these have that x of 1 is less than x of 2, x is less than x of 3. That may not be the case at all. In fact, x of 1 and x of 3 could be the same. Okay, but we do have to have these to be points to be non they're not linear, not collinear rather. Okay, but then we connect them and we have our triangle. So we're trying to find the area of this triangle. So in order to find the area of this triangle here, I'm going to go about it kind of a strange way, but I'm going to find the area of three trapezoids. And my first trapezoid, I'll just call trapezoid number 1, is going to be here. It's going to be going from the point x sub 1, y sub 1 down to x sub 1, 0, which is right here on the x-axis, over to x sub 3, 0, and then up to x sub 3, y sub 3, and then back. So I'm kind of outlining it. Do you see this purple trapezoid? Okay, it's got two parallel sides, and then so what is the area of this trapezoid? Trapezoid number 1. Well, it's 1/2. Little b would be this length, and what's this length? It's the height, right? y1, right? It's y1 is little b, and big B is what? y3. And then what's the base here? Well, the base would be what? X sub 3 minus x sub 1, the difference of those two. Okay, and I'm going to go ahead and do the foiling, so to speak, over here. So this is equal to 1/2, and I'm going to foil y1 times x sub 3, but I'm always going to put the x first, so x sub 3 y1. Since they're real numbers, I can commute them, the multiplication of real numbers. That's the first. Outer is negative x1 y1, and then inner is x3 y3, and last is minus x sub 1 y sub 3. Okay, so just expanding that out. So that's the area of our first trapezoid. Our second trapezoid, I'll outline in green. Similar to this one, I'm going to start at x sub 3, 0, and come over here to x sub 2, 0, up to here, and over to here, x sub 3, y sub 3, and then back down. So you see that trapezoid there? What's its area? The little b there, or big B, I don't know, we'll just say this is what? This is, well, we'll just say y sub 3, right? Y sub 3. And this side length is y sub 2. So there's big B plus little b, or little b plus big B, however you want to look at it, the length of those two sides, right, from this trapezoid. And then we need the distance this way, the base area here, which is x2 minus x3. Okay, and again, I'll expand this out. Y3 times x2 is x2 y3. Outer y3 x3, so minus x3 y3. Inner plus x2 y2, and last minus x3 y2. Okay, so there's that one. And then one more to do. I'll do this one in blue. So trapezoid number 3, and this one I'll start again at x1, y1. I'll go down to x1, 0, and then all the way across to x2, 0, up to x2, y2, and then back across. So here I'm sort of outlining this one. It's kind of the area in a way beneath our triangle and above the x-axis in a way, right? So that's our trapezoid number 3. And so what's its area? Okay, this length is y1, and this big B is what? y2. And then our base is x2 minus x1. And again, I'll expand this out. First is x2 y1. Outer is minus x1 y1. Whoops, x1 y1. And then x2 y2 is the inner. And last minus x1 y2. Okay, So what is the area of our triangle? Area of the triangle. Well, I'm going to do it in terms of the areas of these trapezoids. Notice it is the area of the purple trapezoid 1 plus the area of the green trapezoid 2 take away, right, the area of blue trapezoid 3. You see that? So it's going to be number 1 plus number 2 minus, these are number signs, sorry. So add those together and subtract number 3. Okay, so we've got a little bit of algebra mess to do and to simplify. And so I'm just going to write this out. Notice each one of these has a 1/2 factor. So let's pull that out of all of them. And so area 1, I'm just going to write that out. Plus area 2, I'm going to write that out. And then minus this one. So I need to change the sign of all these, right? So let's do this. Here's rectangle or trapezoid 1, copying from up here. And then adding this one. And then subtracting these. So I'm going to change the sign of all these so it becomes minus x2 y1 plus x1 y1 minus x2 y2 plus x1 y2. Okay. Whew. There it is. But now we do see some simplifying, and if you look in there you'll see some like terms, and they're actually the ones where the subscripts are the same. So look at negative x1 y1 and positive x1 y1. So those combine to 0. Positive x3 y3, negative x3 y3. Those are gone. And then positive x2 y2 and negative x2 y2. Okay. And so we're left with 1/2. Just write the things that are left. Okay. So we have this. Now here's what we've got down to, so algebraically. Now remember what we're trying to say that this area is equal to this determinant. And so what I want to just do now is actually come over here and take a look at this determinant and see what we get. Okay. And I'm going to use 1/2 here, and we'll talk about the negative in a minute. And the way I'm going to find this determinant, since it's a 3×3, is I'm going to use that technique, permutations approach. I'm going to recopy the first and second columns here. And you remember how we can do this? We take the product of 3 entries, and those entries have to be in separate rows and columns, right? So there's a 1/2 here, so factor that out. So I've got x1 times y2 times 1, which is x1 y2, and that's a positive product. And then y1 times 1 times x sub 3 is positive x3 y1, and then here x2 y3. Remember this technique. And then I can do the ones going in the opposite direction, right? This way. We'll do these in red to indicate that those are negative ones, right? Negative x3 y2, x1 1 y3, so negative x1 y3, and then lastly this product. So that's the determinant, right? And let's compare that determinant with what we have here. Okay, pull this down here. Let's compare that determinant with what we have here. And of course we got the 1/2. x1 y2 positive is over here. x3 y1 is there, x2, y3 is there, and then the negatives, x3, y2, negative x1, y3, negative x2, y1. And these are the same, just a little rearrangement. So we've proved it. Now there is this fact about this plus or minus deal. So what about the negative? Where's that coming into play? Well, I drew this in a particular way, right, where x1 or x3 was between x1 and x2. But if I moved x3 out here, right, then we will see the sign might change, and so that's why we need to include the negative there. Okay, so this determinant almost works, right, but there's certain configurations where the number we get comes out to be a negative 1 times the area, and so we can correct that by changing the 1/2 to a negative. And so this proof obviously is for a certain setup where x3 is between x1 and x2, but in general we might have to have that negative 1/2. Okay, so that was kind of a tedious little bit of a proof. I mean, lots of geometry and algebra, but once we get there, it's a pretty nice thing. And so let's apply it now. This will go much quicker. Let's apply this to some examples. So let's find the area. Pull that up there now. Let's find the area of a triangle whose vertices are 1, 0, 2, 2, and 4, 3. Okay, so I'm going to form this matrix. So it's x1, y1. There's x1, y1. So 1, 0, and then always a 1, 2, 2, and a 1, 4, 3, and a 1. Okay, so let's first compute this determinant, and I'm just going to say, again, you can use cofactor expansion along row 1, for instance, or column 2, but I'm just going to do this with the calculator. And I'm going to get negative 3. Okay. And you can, if you want to practice, computing the determinant by cofactor expansion, please do. But for this type of exercise, you can do that. But here's the thing: since this came out to be negative, what do I need to do to choose here? So I choose this, right? I choose whether it's positive or negative. I have to choose this to be negative. So I have to choose negative 1/2 to multiply this thing, so that I get negative 1/2 times negative 3. The area is positive 3/2 or 1.5. Okay, so there's the area of that triangle pretty quick. I mean, that's a very efficient method. If you can remember this matrix and how to do it, then this is kind of a neat little way to find the area of a triangle. A couple other things I want to talk about in view of this. Then let's talk about the following. How do you determine if 3 points are collinear? How do you determine if 3 points are collinear? There's ways you can do that using vectors, creating 2 vectors with two of the points create a vector, and then another 2 points create a vector, and make sure that those vectors are collinear, for instance. And we talked about vectors being scalar multiples of each other if they're collinear. So I mean, there's things you can do, but now with what we just learned, why does this work? That these 3 points are collinear if and only if this determinant is equal to 0. Why would that be the case? How is this true based on the previous application? Well, remember, this determinant would find the area of the triangle, and it says these 3 points, the area of the corresponding triangle is 0. How is that possible? Well, the idea is then these points, there must not be a triangle. These points must be on a line. They must be collinear, right? That corresponding triangle would have an area of 0. And so this is a nice little application to test if 3 points are collinear in the plane, if they lie on the same line. Okay, and then with this, then we can also move to this, which is the equation of a line. Now, a lot of you know how to find the equation of the line, y equals mx plus b, the point slope form or the slope intercept form. But this again goes back to this equation. The equation of the line passing through the distinct points x1, y1, and x2, y2 is given by this equation. Notice I've got x and y here. These are variables. Okay, So why is this similar to what we just did? I mean, I thought it was x1, y1, x2, y2, x3, y3. Well, now we have just 2 points. They're down here. This is an arbitrary point. But if this point xy is collinear to x1, y1, and x2, y2, then this determinant must be what? 0, right? That's what we just said. So notice this will be given an equation, right? So how does this follow from this fact? This will force these 3 points xy, x1, y1, x2, y2 to be collinear, to lie on the same line. And with that, I'll have an equation in the variables x and y. Okay? So for example, we'll close with this. Find the equation of a line passing through these points. Well, the equation would be x, y, 1, and then 2, 4, 1, and then negative 1, 3, 1. That determinant equals 0. Well, there's your answer. I mean, that's the equation, but obviously if you're doing an algebra class, they're not going to want that answer, right? They're going to say, what is it? Y equals mx plus b. What is that? Well, I mean, we can now do it. So let's do this. We'll do now this time, since there's variables, we'll go ahead and do the cofactor expansion. And we'll go along, there's no zeros, we'll just go along row 1. Along row 1. So I'm going to have x times its cofactor, which is a positive 1, times that, and then plus y times its cofactor, and y's cofactor is going to be negative 1, right, to the 1 plus 2, negative 1 cubed, so it's negative 1 times that minor, the determinant of that matrix. So it's going to be negative 1. I'll just put that negative 1 by doing a minus sign here, and its minor is 2, negative 1, 1, 1. So don't forget that, plus minus for the cofactor. A lot of times that's forgotten. There's the minor. And then 1, so positive 1 times its minor, which is right there. And all this is equal to, again, 0. That determinant has to be 0. So what do I have? X determinant here is 4 minus 3. Determinant here is 2 minus a negative 1. And determinant here is 1 times what? 2 times 3, 6 minus a negative 4. So this is, of course, 1. I get x. This is 2 minus negative 1 is 3, so I get minus 3y. 6 plus 4 is 10. And there's the equation. If you want to solve for y, you can. You can solve for y if you want to put it in slope-intercept form. But that's the equation, and there it is. And so this maybe is not as fast as you could do it, but it's comparable, right? I mean, you have to find the slope first, and then you plug in to get your y-intercept essentially, and get your equation. But just some neat little things, I thought. There's also similar extensions to ideas that you can do with determinants of involving three-dimensional space, volumes of parallelepipeds and things called parallelepipeds, which are like an extension of a parallelogram into 3 space, and other things, distances between points in a plane, distances between planes, all sorts of things. But I just thought I would highlight this kind of neat stuff. And again, if you can remember this little matrix and how it helps you with finding the area of a triangle, whether points are collinear in the equation of a line given 2 points, I think that's kind of neat. Okay, so we'll close here. That's another neat little application, some geometric applications of the determinant.